So I'm going to ask you to stop the video and have a go at this exercise. I would like you to calculate the oxidation state of the atoms in all these compounds, and using the rules I've mentioned in the previous slides. Stop the video now, please. Okay, I hope you stopped the video and had a go at the exercise. How would I go about calculating these oxidation states? Well, I stick to the rules. So the first compound, H2S, would be sulfuric acid if it was in solution, of hydrogen sulfide if it's in gas form. So I have the hydrogen there. It's not attached to a metal, especially not for the first and second group. It's attached to the sulfur. So I've got the oxidation state of the hydrogen is going to be +1, because that's the typical oxidation state of hydrogen, except when it's attached to metal ions, especially first and second group of the periodic table. Now I look at the sulfur. Well, I've got 2 hydrogens in my compound, and each of them has lost control of 1 electron. And that compound is neutral, so there's nothing else around that. It doesn't have any charge. So the only way of that hydrogen to have lost, those 2 hydrogens have lost control of 1 electron each, with respect to how they would be in if they were on their own, is for the sulfur to have gained control of those 2 electrons. And I look at it and I say, yes, because if I have 2 hydrogens with an oxidation state of +1, and I've got the oxidation state of the sulfur, it needs to add up to 0. So yes, the oxidation state of the sulfur needs to be -2, because that's the only one that would satisfy that equation. Second compound, S8, so sulfur I think this is yellow sulfur. Well, it says atoms of sulfur, they are only attached to other atoms of sulfur. They don't control more or less electrons that they would if they were on their own, because they're attached to other atoms that are identical. So the oxidation state of the sulfur in this compound is going to be 0. Next compound, sulfur dichloride. I look at the sulfur and the chlorine, and the first one I can identify more easily is the chlorine. The sulfur, we have seen that it changes. The chlorine doesn't change. The chlorine is always -1, except when it's attached to oxygen. And in this case, it's not attached to oxygen. So the chlorine atoms have, in a compound, except if they're on their own or attached to oxygen, have an oxidation state of -1. And now I use that information to calculate the oxidation state of the sulfur. So overall, it's a neutral molecule. So overall, those oxidation states have to add up to 0. I've got chlorine. I have 2 atoms of chlorine. So I've got 2 times -1. And I've got the oxidation state of the sulfur. And if I solve that equation, I find that my sulfur in this compound has actually an oxidation state of +2, just because what it is attached to. So some atoms can have maybe only 1 or maybe 2 oxidation states. Other atoms can have a very wide variety of oxidation states depending on what atom they're attached to. Sulfur is an example of one of them. It has a very rich variety of oxidation states. It can stabilize depending on what other atom is attached to. It will lose or gain control of electrons depending on the other atom's part of that molecule or that fragment. So if I now look at the next compound, Na2SO3, it's called sulfur sulfide. So I look at the sodium, I look at the sulfur, and I look at the oxygen. Let's start, for example, with the sodium. Sodium has an oxidation state as alkaline of +1. It's an oxidation state that I find very easy to stabilize, and that's basically what it does, except when it's on its own as sodium metal, which is 0. It will always be +1. Then I look at the oxygen, and oxygen, except when it's in the compound, when it's making a peroxide, like for example H2O2, hydrogen peroxide, it has an oxidation state of -2. And now my last step is to have a look at the sulfur. And for that, I need to do a little bit of maths. So overall, this compound has to have a charge of 0 because it's a neutral compound. And I've got the two atoms of sodium that have an oxidation state of +1. And I've got 3 atoms of oxygen, and each of them has an oxidation state of -2. And then I've got whatever is the oxidation state of the sulfur. So if I do some quick maths, this is -6, this is +2. Let's finish off the equation, and I rearrange sulfur. I end up with sulfur has an oxidation state of +4. So in that compound, sulfur has an oxidation state of +4. And as you can see, sulfur, as I mentioned before, has all sorts of oxidation states, depending on what atoms it's attached to. It doesn't mean it's a positive ion with 4 positive charges. What it means, what oxidation state is, if you compare that sulfur in that compound with sulfur on its own, that sulfur has lost control of 4 electrons. They are not being controlled, well, mostly by the oxygen, by the 3 oxygens. So that's what oxidation states mean. It doesn't mean, it can mean, oh, that's the charge of that particular atom because that's an ion. But in most cases, what it means is, if you compare that atom in that compound, it has lost or gained control of electrons with respect to how it would be if it were on its own or with other atoms of the same kind. And finally, the last compound is actually not a compound, it's an ion. It's a sulfate anion. So again, I've got sulfur and I've got oxygen. And the oxygen is not forming part of a peroxide, that's not a peroxide. So oxygen has an oxidation state of -2. And that leaves me with what the sulfur is going to be. Well, the charge, the overall charge of that fragment is not 0, it's -2. That's the charge of the ion. And how am I going to account for that -2? Well, I've got whichever the oxidation state is of the sulfur plus the oxidation state of the 4 oxygens, and each of them is -2. So if I do some maths, this is -8, and that leaves me that you need the sulfur to have an oxidation state of +6 for that compound, that sulfate anion, to have that -2 overall charge. So what does that mean? It means sulfur has lost control of 6 electrons, and those electrons are being controlled by the oxygen that it's making a bond with. So it's not that it has a positive charge and it has lost 6 electrons. What it means, it has lost control of those electrons. And they are now firmly in the hands of the oxygen.